Friday, May 12th. Afternoon. Well, with the weather going the way it is, I figured there's more reading about the heat equation, or a heat equation. Fourier's famous derivation of the heat equation in this book by Enrique Gonzalez Velasco. Where we got to yesterday, the day before, was the heat equation, section 1.8, and up into usual systems of PDEs, ODEs, differential equations, the linearity and superposition of solutions. For each positive integer n, the solution of the heat equation u sub n x comma t equals c sub n e to the quantity negative n squared pi squared kt over a squared times sine n pi over a x satisfies the boundary conditions that x equals 0 and x equals a. If it remains to see if any of these satisfies the initial condition. We have u sub n x comma 0 equals c sub n sine n pi over a x. And it's clear that no u sub n satisfies the initial condition unless this is of the form f of x equals big A sine n pi over a x for some constant a and some n, a very unlikely occurrence. Does this mean that the method of separation of variables has failed and we should look for a solution elsewhere? Not necessarily, because as we shall presently show, the heat equation is linear, and this will enable us to try a linear combination of the preceding solutions in order to solve the complete boundary value problem. A partial differential equation is defined to be linear if and only if the following conditions are satisfied. 1, if u and v are solutions, then u plus v is a solution, and 2, if u is a solution and r is a real number, then ru is a solution. So linearity is, in this sense, being membership in a vector space of these solutions. Whereas that in the existence of zero, the zero vector, and about that is the definition of what a vector space is. Example 1.4, the heat equation is linear because if u sub t equals ku sub xx and v sub t equals kv sub xx, then quantity u plus v sub t equals u sub t plus v sub t equals k u sub xx plus kv sub xx equals k quantity u plus v sub xx. And for any real number r, quantity ru sub t equals ru sub t equals rku sub xx equals kru sub xx equals kru quantity xx. The second partial derivative with respect to x. Example 1.5, the equation ut plus u sub x equals u sub xx is not linear because if u is a non-constant solution and r not equal to 0, 1, we have r sub ut equals ru times ru sub x equals ru sub t plus r squared u sub x is not equal to r ut plus ru ux equals ru xx equals ru quantity xx. This violates the second linearity condition. Now, from the earlier talk, basically I was looking at figuring out the quantities a little bit, like what sits in the exponential and what sits in the trigonometric part, and I really need to refresh my understanding of the derivation of that part a little bit about why it's possible to line up the exponent and the sign in that manner that in terms of periodic solutions to these kinds of things that ends up making the attenuation out as of that part or that bit, and as to why the sinusoidal part applies oppositely as in a sense to the exponential part, which makes its kind of its front and back end of what's something that diminishes or grows in terms of the differential equation of usual sorts, where it's kind of along as the lines that it was figured as from when the distance goes to 0 and adding that back up, that after the trivial solutions there was a couple kinds of forms, And I'll be interested in getting back to the x squared plus 6kt besides the e to the negative kt cosine x. These kinds of solutions. And I'll need to kind of refresh my basis of understanding and the derivatives as of the course of this, because I'm very interested to get into what are some alternative definitions and how to reformulate the formulas in terms of some of these complementary duals, like sine x. Why not 1 minus sine x when, for example, it's diminishing the other way? Or with respect to otherwise just some possible setups that would help establish then also the idea of the long tail, the long fall, or the long drop, where the idea is it drops what looks like it's linearly, and then it drops down to 0 very rapidly and very slowly, then reaches a point finally, then it drops off at the end. And so the traditional method would end up just having a diagonal line from 0, 1 down to 1, 0, where the idea is that it looks a lot more like 1 over x, as if scaled from the quadrant into that corner of it or whatever. So it still goes from 1 or 0 comma 1 to 1 comma 0 x and y coordinates, but that it does so, it's mostly in the very beginning it drops all the way mostly to 0 and then it ends up near to 1, or otherwise as for example inflection the other way. And in terms of those two kinds of things, trying to figure out how to box that up, making up for what would be those two kind of components as would add up into each other, in terms of that being kind of like the far corners of this diagonal that basically reflects that there is a gradient. It is a drop. It is a unit drop. And to get figured how to rewrite some of these things from their derivations and definitions this way, which work up the Fourier series, and as to other ways that also happen to sum up to this thing. And so that gets into like these notions of what about the complete ordered field? Well, you know, it's unique up to isomorphism. What does that mean? Well, we had a result in abstract algebra that made for example, the real complete ordered field and the complex complete ordered field are pretty much the same thing up to isomorphism, of where the operation is like so. And the idea is, well, you can equip -1 to 1, that interval, with the non-standard field operations, so it looks kind of like so. And it's like, yeah, kind of like so. And so it's trying to figure out how to make it kind of like so. That what ends up happening is that something looks like 1 over x, which, you know, starts at infinity and drops until it reaches at 1.1, that point. And then from there, and so at that point, it's kind of, its slope is -1. And then all the long tail goes out until finally its slope is 0. So its initial slope is -infinity, and its final slope is 0. And in the middle, in the course of, as it tracks what was this diagonal line from the point at 0 infinity to the point at infinity 0, that as it goes through 1, 1, the idea is to figure out how to reflect 1 over x and basically make it so that then there are about the root 2, filling those in up to the diagonal, and then making a symmetry case and filling out the box this way. Figuring that looks exactly almost like a vibrating string, as only within a box. And it's kind of a square string in a sense. For some constant a and some n, a very unlikely occurrence. So going on, this we talk about the linearity conditions. It is now easy to see that the sum of 3 solutions, U1, U2, and U3 of a linear equation is also a solution, as it suffices to apply the first linearity property to the right-hand side of the equation. This is a transitivity of sort, possibility to compose things, and because it's closed, this operand that makes for them related concepts are of a type that and it's so, and via induction it's so. In general, and by similar reasoning, the sum of n, big N, solutions of a linear equation is a solution. Combining this with a second linearity condition, we can formally state the principle of superposition of solutions. If U1 through Un are solutions of a linear part PDE, where n is a positive integer, and if c1 through cn are arbitrary real constants, then c1 un plus dot 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 cn un is also a solution. And then he goes on. The relevance of linearity in our case is that the function u of x comma t equals sum from n equals 1 n of cn e to the negative n squared pi squared kt over a squared sum n pi over a x. Is the solution of the heat equation for any positive integer n. Moreover, it satisfies the endpoint conditions because each term in the sum does. In fact, the endpoint conditions of u of 0 comma t and u of a comma t equals 0 for t greater than equal to 0 are also linear. The terms linear homogeneous or simply homogeneous are also frequently used to refer to this fact, in the sense that if they are satisfied by functions u1 through dot 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 un, then they are satisfied by any linear combination of these. Thus, it remains to see if n can be chosen so that our proposed sum of solutions satisfies the initial condition, u of x comma 0 equals fx. Before we this gets into implicits in a sense. Before we settle this matter, it must be observed, because it is quite obvious, that the endpoint conditions are linear by design. If instead we had required that u of 0 comma t equals t1 not equal 0 and u of a comma t equals t2 not equal 0 for t greater than or equal to 0, then these more general conditions are no longer linear. In fact, if u and v satisfy these new conditions, u plus v does not, because u plus v quantity of 0 comma t equals u of 0 comma t plus v, 0 comma t equals 2 t sub 1, it does not equal t sub 1, and rather, that the linearity conditions does not follow. For these solutions that are still solutions, that make for a kind of a generalized outer product of from in the linear space to outside that, or to a degenerate space. This notion of the degenerate, the pseudo, and the quasi. It's thus the same for the other endpoint, for 0 and a, for the endpoints. But this nonlinearity is only a minor obstacle, and the way around it is this. First, define this substitution of the functions u sub x equals t1 plus t2 minus t1 of the quantity of x over a, which is easily seen to be a solution of the heat equation such that u sub 0 equals t1 and u sub a equals t2. If we now find another solution, v of the heat equation, such that v of 0 equals v of a equals 0 and v of x equals fx minus ux, which is precisely the type of problem we are in the process of solving, then the function little u plus big U plus V is clearly a solution of the BVP corresponding to the new nonlinear endpoint conditions. Thus, no generality is lost in assuming linear endpoint conditions. And there are bounds. Returning then to the problem as originally stated, the question arises regarding the initial condition is whether a positive integer n and real constant c1 through cn can be chosen so that fx equals sum of the cn times sine n pi over a x. Again, the answer is no in general, since the sum of trigonometric functions is a very particular kind of function. The sum of trigonometric functions, that's something to be said. When he says it's very particular, I mean, there are only so many identities about the trigonometric functions, and often they're associated with like the square root of the trigonometric functions, the identities in terms of 1 and 0 and each other and x. Vis-a-vis, that's when the identity is parameterized or it has a free variable, whereas otherwise, you know, they're the values of sine and cosine. And we're not going to talk about the linearization of the case when as sine x and x, as x goes to 0, that sine x over x equals 1. Which is, ever since I learned how that was derived, I thought it was kind of bad. And it's like, well, actually, yeah, everybody uses what's called small angle approximation, that this sine over x as x goes to 0 equals 1. And I'm not too sure about that. It's accurate, though. It's kind of like this idea of this 1 over x, and that at 1, 1, its derivative is -1. And its derivative ranges from negative infinity to 0, and that for about half the terms, on the up, the half the terms, because it's symmetrical about the x equals 1. X equals x. It's symmetrical about x equals x, or drawing through the first quadrant there. And so half of that branch is above that and before 1, and half is otherwise. Where the idea is you model that square, and something coming from 0, 1 to 1, 0, as instead modeling it as by, looks like 0 infinity, and goes to infinity 0, and then it comes through that point. Then that 1 plus x, and then another function that happens to have the same kind of form, but is kind of drawn up to that diagonal that doesn't exist at the point of infinity. So that 2, 2, and 3, 3, or 2, 2, and or otherwise in squares or cubes or some other powers probably, goes up to that. Then there's a way to work up for the factorial or the powers in the numbers, to build another kind of complement to these kind of orthogonal systems, which makes for, I'm just trying to figure out this non-standard way to add up a series of these functions, to add up something new and make it kind of interesting. Since the sum of trigonometric functions is a very particular kind of function. The answer is definitely no if f is not differentiable, even if it is continuous, because the sum of the trigonometric functions on the right is differentiable. What Fourier proposed is an infinite sum, and claimed that for any arbitrary function f, it is possible to find constants c sub n such that f of x equals the sum from n equals 1 to infinity of c sub n sine and pi over a x, even if f is not differentiable. The same assertion had been made much earlier by Daniel Bernoulli in connection with a different problem, but unlike Fourier later on, Bernoulli did not attempt any mathematical justification of this idea, which was overwhelmingly rejected by the mathematical authorities of the times. As we have already seen, Fourier experienced a similar kind of skeptical opposition. The main obstacle in accepting that an infinite series could add up to an arbitrary function was precisely the concept of function then in vogue at the turn of the century. Because of the success of the calculus of Newton and Leibniz, mathematicians grew accustomed to functions being given by analytical expressions such as powers, roots, logarithms, and so on. We call these elementary functions in terms of Ruffini-Abel. In terms of that, the elementary functions are all you need in their closed forms to solve up to quartics, and then some quintics are not solvable by elementary functions, or these analytic expressions that define functions that had parameters and given orders. How, they demanded, can a function such as f of x equals e to the x be represented by the sum of an infinite series of sines? Why, this function is not even periodic while the sine functions are, and consequently so is the sum of a series of sines. Since a function such as an exponential cannot coincide with a periodic function over the whole real line, they failed to realize that this could happen over a bounded interval. It's going to bounds. Of course, things change if a different geometric as opposed to analytic concept of function is adopted. For instance, a function may simply be given by its graph in the plane, whether or not there is an analytical expression for it. Then two different functions, such as those in figure 1.2, can be identical over a bounded interval, but not outside. Fourier was confident of the basic truth of his assertion that the sum of a trigonometric series can equal an arbitrary function or a bounded interval, and gave numerous examples in which this is geometrically evident. Example 1.6. Figure 1.3 represents several stages in the addition terms of the series. The sum from n equals 1 to infinity of 2 times the quantity negative 1 to the n plus 1 over n sine nx, or the interval 0 pi. The larger the number of terms incorporated into the sum, the closer the addition seems to get the function f of x equals x on 0 pi. The same is true since every term of the sum is odd on negative pi 0. Of course, the sum of the series is periodic of period 2 pi, and its graph is continuous at each point in the form n plus 2k pi with k many integers is a straight line y equals x only on negative pi pi. So this gets back into the n pi over a. It gets into breaking down this boundary in terms of, then you get that in the units instead of the usual period at 2 pi of the sinusoidal curves, sine and cosine, and then there's this k, this constant k, Oh, it is of that the graph is of pi plus 2k pi, or rather pi plus k 2 pi, so k just represents the nth period, say, or the n minus 1th, with k an integer, dot dot dot. While Fourier's arguments and examples were overwhelmingly and sufficiently convincing to merit the Institute's prize for 1811, the fact remains that he did not provide a mathematical proof of his assertions. We shall devote the next chapter to the study of the convergence of trigonometric series and the conditions in which their sum can equal an arbitrary function. It is only after these facts are established in solid mathematical ground that we shall return to the problem of the heated bar and other problems based on the use of identical or similar series. Now, as we're doing that, there's been a couple other quick things. At one point he said whence, and I was like, whence is not necessarily hence. Whither and whence, because there's an idea about something that could be considered another way, or replaced with an alternate derivation that would give it later different kinds of conditions. But it's something that I will scratch my chin a bit more about later, as we get to reading a bit more about the conditions of the summation of these orthogonal functions, sine and cosine, and their series of one of these with regards to making the Fourier series, and about how that works in any given boundary in terms of the time and the frequency, or the time, the space components, that it will be a usual and pretty general thing to get figured out how this can be a regular part of the grab bag toolkit of the differential analysis. Well, I didn't find what I was looking for yet by the time I got back to a posteriori check, so it was somewhere I thought before that, and it's something that I'll get to later on. Just kind of like when I mentioned that there's these ideas of these other families of functions kind of establish the linearity of the space, or establish the superposition of solutions and this kind of thing, that there's other kinds of ways to try and get into it at that sort of avenue, what could help make up what would be the complements, these complementary duals in these other spaces, that then it can establish similar terms in said series about similar bounded regions, or translations, or bridges in effect, and these kinds of great things, making for alternative derivations that would have their own special character, and then would admit in closed forms what our other systems are not closed forms, and make fungible and tractable in some closed forms what are otherwise not fungible and tractable in other closed forms, and then explaining how it's possible to translate or transform them to set them up either way and make them work together. And then as to whether that usually fits only highly contrived solutions, or it fits usually most of the rest of the part, that the two together make an original and bounded kind of analysis to help square things up. Yeah, that would be the goal, of course, but usually it's only partially accomplished. Historical epilogue. So the next chapter will be, there's a bunch of exercises, and it would be a great thing to do to, first of all, recall the other and the rest of the course, and then get into the Fourier series. But chapter 2 is Fourier series. It's got a picture of Augustin Louis Cauchy. The book started with a picture of Fourier. And the chapter 1 ends with an historical outline of the surrounds of Fourier in 1814 to 1816, and the French Revolution, and his entry to the Royal Society of London and the Académie Française in 1826, and his end in 1830. following on, there's a hypergeometric form. There's various example. And then chapter 2 begins about Fourier series. 2.1 Introduction. Fourier died without having been able to prove that an arbitrary function can be represented by a convergent series of trigonometric functions. This seems to be so because you can contrive a series that's arbitrarily small, and if you use something like the small angle approximation or something like that, you can make that arbitrarily small. And so you can say that there's arbitrary analytical character in each range, and then that you can basically move the filter over a given piece of the period or the bounded region from being able to map this function basically 1/2 period. So it's just a bunch of different humps, kind of, that then it's possible to add up these humps as lumps as have been so divided and given arbitrary analytical character to give an existence proof that an infinite series of sine and cosine parameterized all by one variable, but having arbitrary constants for each, could add up to match any smooth function across that way. And that's similar to the idea of this 1 over x shrink is the idea to pull 1 over x down and look at it as the whole quadrant like a unit square. And so, well, what do you mean look at the quadrant like a unit square? Well, its behavior is that it starts at 1, 0, or 0, 1 rather, as if it were 0 infinity in the quadrant, and then it comes down to 1 over 1, and then it goes out to infinity 0, or it goes out to 1, 0. So what it does is it looks like a straight line pretty much dropping down from the one side of the box, but there's it's like a hump that's all the way full instead of the sine wave that's arbitrarily small, and then you add those up to arbitrarily small constants. And then the idea is that there's some way to reflect or pull that into, it goes to the diagonal. And so the differences from the diagonal is kind of like this infinite series the other way. And then that basically reflects the same kind of quantity of something that reflects, this half of a sine waves period, which is just kind of an everywhere positive hump that you can use to add up to make a given particular set of values. That it's possible to make it so like this, about some arbitrary function represented by a convergent series of, that's not a trigonometric function, that's more of a non-standard function from the realm of converting a quadrant to the unit square. Actually, when his prize essay was found to be faulty on this grounds, there was no workable definition of convergence. So convergence is usually the notion of the limit. Surely the concept did exist. We have only to recall that about 1360, Nicole Oresme, Bishop of Lisieux, had shown the divergence of the harmonic series. Even the words convergent and divergent were available, introduced by James Gregory in 1668. But vague ideas and words can get one only so far in mathematical proofs. Mathematics deals with quantities and comparisons between quantities, with equalities and inequalities. What was needed was the definition of convergence involving comparisons between the partial sums of a series and its proposed sums, such comparisons to be established by means of inequalities. And this is where, besides the usual great facility of the trigonometric functions, because everybody had a chance to learn them, and they're available via classic constructions, and everybody had to learn them, so everybody at least knows some of them and most about them, is these other families of orthogonal functions that build up all the things that make up for the Hankel transform, the Mellon transform, the Z transform, and ... besides the Fourier transform. As it happened, one of the first workable definitions of convergence was given by Fourier himself in his prize essay of 1811, later incorporated into his book of 1822. He stated that to establish the convergence of a series, it is necessary that the values of which we arrive on increasing continually the number of terms should approach more and more a fixed limit and should differ from it only by a quantity which comes less than any given magnitude. This limit is the value of the series. Of course, the methods of exhaustion are since antiquity, and Zeno's paradoxes are framed both as an argument against the infinitely divisible and for finite numbers, and also as be a deduction that the limit exists and can be well defined. The use of inequalities is already implicit and is less than any given magnitude. The real numbers are trichotomous, trichotomy, that can be cut, and any different cut or difference makes it so that two real numbers are either equal or they maintain intransitively less than and greater than relations, i.e. if two numbers are less than, then any number that is established less than another number is also less than any numbers that it is less than, and so on ad infinitum. And similarly for the greater than. Now, clearly, greater than and less than are two separate things that transitively compose to maintain trichotomy. And then there's greater than equals and less than equals, and gets into the notion of the strictly increasing or strictly decreasing functions, or for the increasing decreasing functions, which are just in some senses non-decreasing and non-increasing. But that is so about the notion of the limit, and when we have things go to the limit, and also from above and below, that they would be about the same. And then there's the expanded definition of limit these days, besides that it is always the case that it never goes away from the limit, that it always is like smoothly, continuously, constantly diminishing in distance from the limit. There's this situation where the convergence can be defined that when it overshoots but then comes back, and as always the overshoot is less and less, then finally it also reaches the limit in this way, or it's like sine x over x or something like that. More precise and definitely more influential was the definition of convergence given by Augustin Louis Cauchy, often referred to as the father of modern analysis. And indeed he was, for he was the first to understand the importance of rigor in analysis, and the first to consistently use the language of inequalities, starting with his definitions of limit and continuity. To him we owe the use of the letter E to denote the error of the approximation between a variable quantity and its limit. The error term. I don't know who came up with delta epsilonix, but the delta epsilonix is the usual milieu of the fundamental proofs establishing the limit, and also the fundamental theory of the derivative when the delta h goes to 0. Cauchy was well aware of the work of his predecessors and contemporaries, and in particular Fourier's work, but he was not given to quote any of his sources of inspiration. We do not know whether or not Fourier's earlier definitions of convergence was instrumental in shaping Cauchy's own ideas. What we know is that once in possession of a rigorous definition of limit, Cauchy published what is essentially the modern definition of convergence in his 1821 textbook Cours d'analyse de l'école royale polytechnique. It was later written in fully modern terminology by Edward Heine, H-E-I-N-E, Heine, in 1872, and this is the version reproduced in Appendix A. But what is more remarkable about Cauchy's contribution is that he did not limit himself to stating the definition of convergence, but immediately, one page later, he started giving theorems containing tests for convergence, the so-called Cauchy criterion, already anticipated by Bolzano in 1817, along with the definition of continuity and the root and ratio tests. Further tests were given later by several other mathematicians, among them R-A-A-B-E, Abel, Dirichlet, and Weierstrass, thereby building a solid theory of the convergence of series that could be applied in many practical situations. A proof of the convergence of Fourier's trigonometric series was attempted by Poisson in 1820, by Cauchy in 1823, and of course by Fourier himself throughout his life. He never succeeded, but one of his sketches for a proof would be of value to the man who finally did. The analytical theory of heat, it says. In the summer of 1822, a Prussian teenager, Johann Peter Gustav Lejeune Dirichlet, from Düren in the Rhine province, came to Paris, attracted by the presence there of so many luminaries in the field to study mathematics. He became acquainted with Fourier, who encouraged him to work on trigonometric series and showed him his sketch of the convergence proof. It would be some time, however, before Dirichlet could complete a valid proof, his main interest being outside the field of applied mathematics. He left Paris in 1827, and the following year started teaching mathematics at the General Military School in Berlin. Then in 1829, he published a paper entitled Sur la convergence des séries trigonométriques qui servent à représenter une fonction arbitraire entre des limites données, on the convergence of trigonometric series that serve to represent an arbitrary function between given limits. Here, after replacing a certain trigonometric identity in Fourier's sketch of proof with one of his own, see lemma 2.1, he succeeded in giving sufficient conditions for the convergence of Fourier's series, namely that f have a finite number of jump discontinuities, and a finite number of minima and maxima. In this chapter, we shall give sufficient conditions for the convergence of these trigonometric series and present some related results. There's some question about whether you need one or the other, sine or cosine. It's like, well, it's kind of deflated all at one end, or it's like all its characters on one end and not the other. I mean, we kind of would need to use these both. Oh, it does have both. Yeah, here we go. The main question is whether or not a given function f defined on an arbitrary interval, alpha minus a, alpha plus a, greater than 0, can be represented by the sum of a convergent series of trigonometric functions. Actually, we can reduce this to a somewhat simpler problem. Given a function f of negative pi to pi onto r, it is possible to determine coefficients a sub n and b sub n, or a n and b n, such that f of x equals 1/2 a naught. This is the first constant term, the offset, and then sum n equals 1 to infinity of this quantity, a n cosine nx plus b n sine nx. The coefficients for cosine and the coefficients for sine, and those added up together. So you have these two sequences that define these coefficients for every x in negative pi to pi. The reason why a naught is multiplied by 1/2 is purely technical and will be seen below, because it's kind of the same for b naught is built into it. As for the restriction to the interval negative pi pi, motivated by the fact that the trigonometric functions are periodic of period 2 pi, it is actually not significant. It will be dealt with in 2.5 by introducing a new variable, y equals pi over a times the quantity x minus alpha. That varies from negative pi to pi as x varies from alpha minus a to alpha plus a. Establishing this centrality is about where the two half periods come together. That the period is as of half the period is in there as bounded by -1, 0, and the other one by 0, -1. With the idea of figuring out these field operations for -1 to 1 and figuring out this quadrant shrink to the unit square of 1 over x, about ln x and this kind of thing, and differential. The determination of the coefficients a sub n and b sub n is a simple matter if certain assumptions are made. Assume that the series in 1 converges and that equality holds. All this, of course, remains to be settled. Assume further that the series can be integrated term by term from negative pi to pi, and that the same is true both sides of 1 are multiplied by either cosine mx or sine mx, where m is a non-negative integer. Then if we multiply 1, that was the formula, was 1, f of x equals 1/2 a naught plus the sum of n equals 1 to infinity of this quantity, a on cosine nx plus bn sine nx. Then if we multiply that by cosine mx, we get the integral from negative pi to pi of fx cosine mx dx equals so taking the integral of that as the product of the function and then multiplying that by both sides, basically this cosine mx equals 1/2 a naught, the integral from negative pi to pi of cosine mx dx plus sum from n equals 1 of this bigger quantity, a n integral from negative pi to pi cosine nx cosine mx dx plus bn integral from negative pi to pi sine nx cosine mx x dx. If we recall the well-known formula, the integral from negative pi to pi of cosine mx dx equals 2 pi if m equals 0, and 0 if m not equals 0, and that the integral of negative pi to pi of cosine nx cosine mx dx equals pi if m equals n, and 0 if m not equals n, and the integral of negative pi to pi of sine nx cosine mx dx equals 0, we obtain a sub m equals 1 over pi integral from negative pi to pi fx cosine mx dx. M equals 0, 1, 2, dot, dot. The reason for the coefficient 1/2 and 1 is now apparent. Without it, the previous formula would not be valid for m equals 0, and a separate formula would be needed. Without it, the previous formula would not be valid for m equals 0. A similar procedure, but multiplying 1 by sine mx yields b sub m equals 1 over pi, integral from negative pi to pi, fx sine mx dx. M equals 1, 2, 3. Oh, so kind of the a on the cosine is left out in the front, and the b is only contained up in the higher order one. So they kind of alternate in that sense. In terms of then how they're built up in these terms is about these well-known formulas, which basically then these well-known formulas are what are used to build up for the orthogonality conditions, the same kind of things for other orthogonal formulas. The simple method was defined by Leonard Euler in 1777, but only after having first obtained these formulas in a more complicated manner. Fourier arrived at the same result independently, also discovering the simple method after a much more complicated one. There is no reason to believe at this moment that the assumptions made above on the convergence of the series 1 and the term-by-term integration are valid. But whether or not they are, this will be decided later on. We take the resulting formulas as our starting point. If the following integrals exist, the numbers, the a sub n's and the b sub n's, are called the Fourier coefficients of f on negative pi to pi. The series 1/2 a sub naught plus n equals 1 to infinity of this quantity, a sub n cosine nx plus b sub n sine nx, where a sub n and b sub n are given by 2 and 3, is called the Fourier series. Of f on negative pi to pi. That is a series, a sequence is an infinite list of values, and a series is the sums that is basically that the series is as a result of summing incrementally each piece there. So that calling that the Fourier series, it indicates that it's got these coefficients as or the sequence which makes the sum, as in terms of the infinite sum in it. That the a sub n and the b sub n are the Fourier coefficients of the Fourier series. Since we do not know yet if and when the equality in 1 that series is valid, we shall use the symbol tilde with the meaning has Fourier series and write f of x has Fourier series 1/2 a sub naught plus 1, or f of x is approximately 1. We shall find the Fourier series on negative pi pi of the function defined by fx equals 0 if pi is between negative pi and negative pi halves, and 1 if it's between negative pi halves and pi for the 3 halves. This graph is represented by this simple function where the between negative pi and pi, the first quarter of it is 0 and the rest of it is 1. According to 2 and 3, we have a sub naught equals 1 over pi, and the integral from negative pi halves to pi dx equals 3/2. And for n greater than 0, a sub n equals 1 over pi, integral from negative pi to pi, cosine nx dx equals sine nx over pi n time evaluated. That's its antiderivative, and then it's computed over that range of integration from negative pi to pi equals sine n pi over 2, that quantity, over pi n equals the negative 1 to the power of n minus 1 over 2 over pi n if n is odd and 0 if n is even. And the b sub n's equals 1 over pi, the integral from negative pi over 2 to pi sine nx dx equals negative cosine nx over pi n, evaluated from negative pi halves to pi equals negative cosine n pi over pi n plus cosine n pi over 2 over pi n equals 1 over pi n if n is odd, and negative 1 over pi n times the quantity 1 minus negative 1 to the n minus 2 if n is even. So I've forgotten kind of some of the derivation that adds up for these, the integrals that make up for these, the sign changes and their powers, as of about just kind of it's about the properties of the quadrants of the Pythagorean, and also going around the circle, this trigonometric sinusoidal function. As pretty cool. Hence, fx is approximately equal to the a naught is 3/4, and the following ones are 1/pi plus cosine x plus sine x minus sine 2x minus 1/3 cosine 3x plus 1/3 sine 3x plus 1/5 cosine 5x plus 1/5 sine 5x dot 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 equals, and then he's written it in terms of an infinite sum of sine and cosine. 3/4 plus 1/pi, sum from n equals 1 to infinity of 1/2n minus 1 of this quantity, negative 1 to the n minus 1 cosine 2n minus 1x plus sine 2n minus 1x minus sine 4n minus 2 quantity x. Sometimes a careful observation of the function under consideration can greatly simplify the computation of its Fourier coefficients. Function f such that f of negative x equals fx for every x in negative pi is called even, and its graph is symmetric about the y-axis as shown in the left in figure 2.2. This reminds me of the involutions and stuff like that. That an even number of negative signs is positive, and an odd number is negative. If f of negative x equals negative fx, the function is called odd, and its graph is symmetric with respect to the origin, as shown to the right in figure 2.2. And so when I'm looking at these even and odd functions, and I'm thinking about the quadrant shrink to the box and symmetry and this kind of stuff, and even and odd, it's interesting to figure out whether even functions would kind of represent one way to represent the even functions and odd functions is with regards to the symmetries and kind of what would add up for those. All these things help me clear that then these result in the middle of the derivation, something gets simpler and it makes it possible. Like so, it should be clear from these graphs that the integral of an even function in a range is equal to twice the value of its integral from 0 to pi, while the integral of an odd function from negative pi to pi, the range, is 0. Since the cosine is even, the sine is odd, and since these facts remain true upon multiplication of these by an even function, but they are reversed upon multiplication by an odd function, the following result has been established. And this also gets into orthogonal functions when one is even and the other is odd, in terms of whether f negative x equals negative fx. If f is the function from negative pi to pi going on to r is such that its Fourier coefficients are defined, that is, if the integrals in 2 and 3 exist, then 1, if f is even, fx has a Fourier series 1/2 a naught plus sum n equals 1 infinity to the an cosine nx. There simply are no b coefficients, where an equals 2/pi, the integral from 0 to pi of fx cosine nx dx. And if f is odd, then fx is Fourier series is sum n equals 1 to infinity of the bn sine nx. So this gets into the case before when you're talking about, well, can we sum up a series of functions and make it so that it's only in the one or the other, the sine or cosine? Well, yeah, if it's either symmetric or antisymmetric about the center of its region. So in a sense that when we talk about a periodic function, oftentimes it's figured out that in the sinusoidal that the first half and the second half are as replicas as if they were symmetrical about the x's. And here this is the idea is, well, how about the center of the range of integration of the bounds? If it's symmetrical about that or antisymmetrical about that, then it can be, you only need one or the other of sine or cosine to make an infinite series that adds up to it. The function defined by f of x equals x on negative pi pi is odd since f of negative x equals negative x and negative equals negative fx. And its Fourier series contains only sine terms. The coefficients are b sub n equals 2/pi integral from 0 to pi x sine x dx. And I'm just reading these off. It's been quite some time since I'd have to recover facility in computing derivatives and antiderivatives, but I do have at least a lot of practice or degree or what. 2/pi equals, in the brackets, negative x cosine nx over n, evaluated from 0 to pi, plus integral from 0 to x of cosine nx over n dx equals negative 2 cosine n pi over n equals 2 times the quantity negative 1 to the n plus 1, or the sine alternation bit, and n over n. Then f of x is approximately, or is sum from 1 to infinity of the quantity 2 times the negative 1 to the n plus 1 over n times sine nx. And so the coefficients are this, the b sub n are the 2 to the negative 1 to the n plus 1 over n. Compare the series with the result with the series in example 1.6 and observe how the sum of the series approaches the given function as the number of terms increases. And here this gets into that adding the first to the part of the series has that the b sub n's often will reduce. I mean, there's something to be said is do the coefficients go to 0? Mostly. And so if you only compute the number for the first coefficients, that provides a value that goes to the value. It's an approximation. It's got an error term. If it's not infinite, it's an approximation. But sometimes there are systems where all the rest of the series coefficients are also 0. I mean, those are like sine and cosine. Does it need an infinite series? It's like, sure, but every single one after the first is 0. Still an infinite series, just everywhere 0. ... So this is getting us more into that is about what's read off, and this book has got 400 pages or 500 pages in it. So by page 30, and it's about Fourier series and analysis, or Fourier analysis and BVPs. So far, this is the definition of the Fourier series. So I'm going to think about that for a while because, and the next is the Riemann-Lebesgue theorem. Let's see here, what has this got about? And it gets into relate this to the development of the analysis a little bit. Let's see. Since the Fourier coefficients are defined by integrals, a brief examination of the concept of integral is in order before we discuss the convergence of Fourier series in section 2.4. Moreover, once the concept of integral is established on a firm foundation, we shall be able to present a result obtained later by a former student at Dirichlet that will allow us to give a shorter proof of a sharper convergence theorem than the original one by Dirichlet. Now, shorter proofs are sometimes good. Shorter proofs are sometimes missing what goes in the derivations that would be separable and distinct. For example, they might have kind of like welded together this one joint in the bottom that enables everything to stand up off it, but then when you need to get underneath that, you got to tear the whole thing out. But otherwise, it's going to be pretty good. Here are the results. The so-called Riemann-Lebesgue theorem is a very powerful tool that we shall use frequently. The popular concept of integral in the 18th century was that of prederivative or indefinite integral. It was sufficient for all their applications and easy to explain. Of course, Leibniz had defined the integral much earlier as a sum and even introduced the integral sign, integral bar s, as an elongated s for sum. However, his idea did not quite catch at that time. So I'm happy that the author at least seems to have the idea is like, is the limit the sum? Well, if there's a sum, it's no different than the limit. And for any of the partial terms, that's the sum. And when you happen to get it so that it only needs finite and min terms, that's the sum. So the only reason we have as a limit is to capture this notion of the sum, and the limit is a sum. And we make these with Riemann sums in the limit. Or the Lebesgue or Stiltes. The popular concept, Leibniz sum. However, his idea did not quite catch at that time. How could it, involving, as it does, the sum of infinitely many, infinitely small quantities? Well, they're all related. They all maintain this nilpotent, or these ratios that are vanishing yet still maintain analytical character. Thus, we come to the 19th century with the notion of integral as prederivative reigning supreme. Fourier changed that, as we have seen, who is used to handling functions not given by analytic expressions, but by curves and pieces of curves, and found the use of prederivatives to be impractical. Instead, he remarked that, for instance, the constant b sub n can be viewed as the area under the graph of 1 over pi of x sine nx, from negative pi to pi, and this whether or not f is continuous. It might have gaps in it, piecewise. Whereas some of the other methods are totally dependent on being just a classical curve and this kinds of things. It may have been, it may have been responding to this interpretation of the integral as an area that Cauchy gave the following definition of the definite integral in his texte Résumé des leçons données à l'École Royale Polytechnique sur le calcul infinitésimal, or lessons given to the school on the infinitesimal calculus of 1823, which we reproduce in the current, more usual notation. If f is a continuous real-valued function on an interval ab, and if x0 through xn are points, so a equals x naught less than ... xn equals b, so a equals x naught and xn equals b, then the integral from a to b of f equals the limit as n goes to infinity of the sum of I equals 1 to n of f of xi minus 1 times the quantity of xi minus xi minus 1. So this is explaining that this sum of the finite differences is the same as the integral. And he said, well, yeah, where it is assumed that for each I, the distance between x sub I minus 1 and x sub I approaches 0 as n goes to infinity. Cauchy was then able to prove, not quite rigorously because he lacked the concept of uniform continuity, the existence of this limit and its independence of the mode of division of a sub b into subintervals. So that the distance between the xi sub minus 1 and xi goes to 0, and also that the distance between any two xn and xn minus 1 and xn minus 1 are the same. Because that, I guess, would be the uniform continuity. All right, then. The existence of its limit is independent of the mode of division, and subintervals. Incidentally, the notation of integral of a to b of f for the definite integral, which Cauchy adopted, is due to Fourier. So Fourier attached to Leibniz's integral bar these limits of integration. I'm not aware of that. Cauchy's definition is quite adequate to prove Dirichlet's convergence theorem for Fourier series. It is true that the functions, this theorem may have a finite number of discontinuities, as we shall see, but there's no obstacle because the given interval can be divided into a finite number of subintervals where the function is continuous, and then the integrals over these subintegrals added together is called piecewise. But Dirichlet knew that he had introduced the requirements of continuity except a finite number of points precisely so that the definite integrals defining the coefficients exist. Consequently, in order to generalize this theorem to functions with an infinite number of discontinuities, which he chose as his next task, he needed only to make sure that they could be integrated. That is what Dirichlet needed, is that what Cauchy's definition did not provide, namely a condition for integrability. Cauchy had defined the integral for continuous functions, but maybe other functions can be integrated as well. Dirichlet never achieved his goal of integrating functions with an infinite number of discontinuities, nor was able to give a condition for integrability. But during the years, he had the good fortune of encountering a very gifted young man among his students at the University of Berlin. George Friedrich Bernhard Riemann had transferred from the University of Göttingen to Berlin, switching from the study of theology to mathematics, and the University of Berlin had a better reputation in this field at that time. Here, Dirichlet was his favorite teacher and was instrumental in shaping some of Riemann's research interests, in particular those on Fourier series and the definite integral. Riemann returned to Göttingen and received his doctorate in December of He wished to qualify for a position without pay at the university as privat docent. He would receive a fee from any students his lectures might attract, but no university stipend. Well, this is just talking about, he wrote an habilitation script which at Dirichlet's suggestion was über die Darstellbarkeit einer Function durch ein trigonometrische Reihe. One of Riemann's goals in his work, printed posthumously, was to give conditions for integrability that would accommodate discontinuous functions. Even this happens at infinitely many points. This end, he modified Cauchy's definition as follows. First, he replaced the factor fx sub I minus 1 by f of t sub I, where t sub I is any point on the subinterval from fx I minus 1 to x. Then, this is more important, he removed the continuity requirement on f. Instead, he turned things around and to find f to be integral if the lim of n goes to infinity of the sum I equals 1 n of ft sub I times quantity xi minus 1 exists, provided that the distance between x sub I minus 1 and x sub I approaches 0 as n goes to infinity, and also with uniform convergence. Next, he stated the theorem giving necessary and sufficient conditions for the integral to exist and to show the wide applicability of his definition. He gave an example of an integrable function that has infinitely many discontinuities on every arbitrarily small interval. All right. Riemann's definition was perfected by Darboux, D-A-R-B-O-U-X. Darboux has got lots of great stuff and identities and dual sums and a bunch of stuff. The man responsible for the dissemination of Riemann's ideas in France, who also proved the corresponding version of the fundamental theorem of calculus. Modern terminology, this definition, which we shall need later, can be introduced as follows. Let x naught through the xn be points in a, b, such that a is equal to x0 and xn is equal to b, and the x sub i's are in order between them. Such a collection of points is called a partition of a, b. Then for I equals 1 to n inclusive, define m sub I to be the smallest real number that is not smaller than any value of f on xi minus 1 over xi. Of course, if f has a maximum on xi minus 1 xi, then m sub I is this maximum value. Assuming that m sub I be the largest real number that is not larger than any value on this. If the function from a to b on to r is a bounded function, is said to be Riemann integrable or simply integrable on a, b if and only if there's a unique number L I such that sum I equals L to n, I equals 1 to n, m sub I of this quantity, the x sub I minus the x sub I minus 1, or the difference in the partition's length, is less than or equal to I is less than or equal to sum I equals 1 n of m sub I x sub I minus x sub I minus 1. For every partition a equals dot 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 through b of a b, this number I is called the Riemann integral of f from a to b and is denoted by integral from a to b of f. So then Darboux went about proving that his definition 2.2, which was see, there's definition 2.1, definition 2.2, which was if it is the same as Riemann's definition above, but that's not the same as Cauchy's definition. So we learned Riemann sums in school, and then there's also Cauchy, and it's to be looked at and figured out how that also works. And it's like, well, it doesn't emit infinitely many discontinuities. It's like, well, then you can piece it up. Well, all right. Hey, that's about what goes into some of these things. I figure I'll try to get some more figuring and work on it later at a later date, and somehow this kind of goes on and still goes. So what I'm most excited about is this idea of the analytical character of among basis functions and sine and cosine and wavelets and other means of support of infinite series of sums as via orthogonal functions and their kinds of transforms. Here it's about these ringing functions or something like that, which instead of thinking about like a function and like its complement in the sinusoidal, like sine and cosine, that one of them is like shrinking the square of 1 over x down to so it looks like that in the field, and how that adds back up the diagonal. And also on the other side of that, it's like, well, you're just going to take a point at negative infinity to infinity and bring that back in. It looks like 1 over x, and you just shrink that whole function of space into a box. And so it'll just start like barely within the square of that box and then shrink and ring into that the diagonal. Yeah, that's my idea. Well, all right. Hey, have a great day.